All right, in this video I want to take a look at using the notion of composition with Taylor functions in order to change the center. Everything we've been working with lately has been essentially Maclaurin series, right? The center was at x equals 0. But what if I wanted to do e to the x, say, centered somewhere else? So let's see how we can do that without, well, e to the x isn't that hard. The derivatives are pretty simple, right? Wouldn't be that hard to just do it brute force. But I want to show you how we can do this with e to the x and then see how maybe we can generalize that to some other things. So here's my Maclaurin series for e to the x, right? Maclaurin series again, Taylor series centered at 0. And what I'm going to do is I'm going to let u equal x minus 3. Okay? That is, I'm going to be trying to end up with this thing centered at x equals 3 rather than centered at 0. Okay? So if x is equal to u plus 3, did I say u equals x plus 3? I want x equal to u plus 3. Then you could, if you needed to, you could solve for u. U is equal to x minus 3. Oh, that's what I did here, right? U is equal to x minus 3, so x is equal to u plus 3. Sorry. All of a sudden my eyes aren't seeing things in the right order here. Notice e to the x is e to the u plus 3 because x is equal to u plus 3. And then because of the properties of the exponential function, I know that e to the u plus 3 is equal to e to the u times e to the 3, and I'm choosing to write it in this order. But then I look at e to the u and I could say, hey, that's just this thing with u's instead of x's. So I'm going to replace that e to the u by the Taylor series with u plugged in. So the e cubed is still out in front, and then I've got 1 plus u squared over 2 plus u cubed over 3 factorial and so on, right? But now u is equal to x minus 3. So all those u's are being replaced by x minus 3's. And distributing the e cubed back in, I've got e cubed plus e cubed times x minus 3 plus e cubed times x minus 3 squared over 2 plus e cubed over e x minus 3 cubed, yeah, there we go, over 3 factorial, and so on, and so on. But notice this really is what we should have gotten to say if we want to center this at x equals 3. Because what I would do, before I did any of this kind of stuff, I would say take the derivative of e to the x, plug in the 3, e cubed. Take the next derivative, e to the x, plug in the 3, e cubed. But, you know, and every single derivative is e cubed. You then take each of those derivatives, divide them by n factorial, and multiply by x minus 3 to that n, right? So here's with the 2, with the n equal 3, n equals 4, and so on. And the e cubes are playing the role of the derivative of e to the x at x equals 3, which is exactly what it is. Okay. So it's nice that we ended up with the right answer there, and we can verify it in other ways. Let's try another example. I want to do this with the function 1 over 1 minus x, but let's center it at x equals 2, right? Before we center it at 0, it's centered at 0, we know that 1 over 1 minus x is 1 plus x squared plus x cubed and so on. So here we go. I'm going to let u equal x minus 2, so x is u plus 2. 1 over 1 minus x, I'm going to replace the x by u plus 2, distributing the minus sign in there, gathering some like terms, factoring out the minus from the bottom, and I've got negative 1 over 1 plus u. But hey, 1 over 1 plus u was the alternating sum here, right? With a minus sign, these were all plus signs, but because this is a plus, now these becomes alternating. 1 minus u plus u squared minus u cubed plus u to the 4th, and so on. Distributing the minus back in, I've got minus 1 plus u squared plus u cubed minus u to the 4th. And lastly, substituting, yeah. Let's substitute the x minus 2 back in here for the u, and I end up with a Taylor series centered at x minus 2, and we started with this was all equal to 1 over 1 minus x. Okay. So we have a Taylor series centered x minus 2, centered at 2. Now I would not expect the interval of convergence to remain the same anymore, because before the interval of convergence was centered at 0, now it's going to be centered at 2. And if you take a look, again, this is a geometric series, so from one term to the next, you're always multiplying by x minus 2. So what we need is we need that x minus 2 to be somewhere between minus 1 and plus 1 in order for this to converge. And that add 2 to all sides here, that means that x is somewhere between 1 and 3. The radius of the convergence is still 1 here. So from the center out to the two endpoints, from the 2 down to 1 or up to 3, right, that is still radius 1, but it's centered at 2 now rather than centered at 0. Let's try another one. It's actually same function, but now this time rather than centering at 2, I want to center it at 3. An interesting thing happens with this one. So exactly the same way we did it before. I'm going to let u, instead of in the last example I said u equals x minus 2, now I'm going to say u is x minus 3. X is u plus 3. The x is being replaced by u plus 3, multiplying the minus sign through, collecting like terms. I'm going to factor a minus 2 out of the bottom now, which is really the whole thing times a half now. But then I've got this 1 over 1 plus u over 2. This looks like the previous one, but instead of just a u there, I've got a u over 2. So the u over 2 is going in place of what was the x originally, right? So 1 minus u over 2 plus u over 2 squared minus u over 2 cubed, so on. Then distributing the minus a half back in there, I get this, and then replacing the u with x minus 3, I've got a Taylor polynomial for 1 over 1 minus x, but now it's centered at x equals 3. The interval of convergence now, though, has changed, because what's the multiplier going from each term to the next? There's a denominator in here, this 2x squared, 2x cubed, 2x to the fourth. So not only is the numerator getting multiplied by x minus 3 each time, the denominator is being multiplied by 2. So the multiplier, that geometric series multiplier getting you from one term to the next all the way down the line, is x minus 3 over 2. So we need x minus 3 over 2 to be somewhere between minus 1 and 1, which means that x minus 3 has got to be between minus 2 and plus 2. Adding 3 to everything, you've got x is between 1 and 5. This is interesting for a couple of reasons. One, the radius of convergence now is 2. Right? This interval has length 4, with 3 right smack dab in the middle. So from 3 down to 1, or from 3 up to 5, that's going to be 2. So we've doubled the length of the thing, doubled the radius of this interval. But I do notice that x equals 1 was the left-hand endpoint before, right? It was from 1 to 3. Now it's from 1 to 5. Coincidence? I don't think so. Take a look at the graph. This is the graph of y equals 1 over 1 minus x. Right? This has a vertical asymptote at x equals 1. When we centered it at 0, the interval of convergence was from minus 1 to plus 1. It stopped at that vertical asymptote. That these polynomial approximations were not going to be able to do anything with that vertical asymptote. So they're only good up to the asymptote, and because of other things, it's only good on the other side for the same amount of distance. So from 0 to the right, you could only go as far as 1. So from the 0 to the left, you could only go as far as 1. When I centered it at 2, again, that's 1 away from that asymptote. So I had a radius of just 1, from 1 to 3. But then when I centered it at 3, it turns out I could get this to converge all the way up to the asymptote again. But the asymptote's still at 1. And so I could go from 1 to 5. You might guess that if I tried centering it, say, at 6, then my interval of convergence would go from 1 up to 11. Right? That is, I'd have a radius of 5 centered at 6, because I'd be able to go all the way over to that asymptote. This turns out to be an important thing, that as you do more of this, at Whatcom, where you do more of this is in a differential equations class. But the location of vertical asymptotes really gives you an indication of how large an interval of convergence you're going to be able to get. If you know where your vertical asymptotes are and you know where you're centering, then the radius of convergence is going to be from where you're centering up to the closest asymptote. In this case, the asymptote's at 1. Okay. Let's do one more example here. This is one that, I'm going to move my face up a little taller here. Yeah, we could do this another way. In fact, we'll look at it another way. But I just want to try the same thing using sine. Right? So we have a Maclaurin series for sine, which is, sine is an odd function, so this uses all odd powers of x. So it looks like x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. It's a lot like e to the minus x, right? So it's got the x to the n over n factorials, but only the odd powers and alternating plus or minus signs. Cosine was all the even powers, right? So here we go. I'm going to try to center this at x equals b. So I'm going to let u equal x minus b. X is u plus b. So the sine of x, I'm going to substitute for the x here, u plus b. Then I'm going to use a property of sine, right? Now, if this was some random function, I wouldn't necessarily know how to handle an x or u plus b plugged in there, right? If it was a square root function, right? What's the square root of u plus b? Is it the square root of u plus the square root of b? No, it's not. Right? This sort of technique will only work if you've got some sort of way of dealing with what does this function do when you put in a sum as an input, right? And I've got a trig identity. The sine of a sum says this is the sine of u times the cosine of b plus the cosine of u times the sine of b. How's your trig? If it's not really good, then you should be saying, well, I'm working at getting it better, because trig is really important. And the properties of these trig functions are just amazing. So at this stage right here, b is a constant. U is my variable. So cosine b and sine b are just constants. So I'm just going to write this cosine b here, and then I'm going to multiply by sine of u, but I'm going to use the Taylor series, or the Maclaurin series, for the sine of u. That is u minus u cubed over 3 factorial plus u to the 5th over 5 factorial minus u to the 7th over 7 factorial plus, and so on. And then here I've got a sine b, so that's there. And now here's the cosine, the Maclaurin series for cosine. So 1 minus u squared over 2 plus u to the 4th over 4 factorial minus u to the 6th over 6 factorial plus, and so on. I can then distribute the cosine b into this first set of parentheses and the sine b into this other one. And what do I get? I'm distributing and combining a lot of things. So the constant thing here is just the sine of b times 1. That's here. There's a linear thing, so cosine of b times u. That's right here. There's a quadratic minus sine b times u squared over 2. So there's my minus sine b times u squared over 2. There's a minus cosine b times u squared over 3 factorial. And then there's a plus sine b times u to the 4th over 4 factorial. All right, so just gathering all of the terms. I'm getting all the odd powers of u from the first one and all the even powers of u from the second one. So just writing them all like this. I want to put one caveat in here just because you have to be careful when adding sums like this. We're going to talk about adding and subtracting sums in the next video. But I'm jumping ahead a little bit here just to show this. You're allowed to add two summations together, two infinite sums together, as long as you are within the interval of convergence. Not on the ends of the interval, but in the interior of the interval of convergence. Technically, if you're in a spot of absolute convergence, then this adding can work like this. And we think about addition being commutative, so it doesn't matter if I take one from this and then one from that and then one from this and one from that. Addition is not commutative if you're not in the inside of the interval of convergence, right? So sine and cosine, interval of convergence is the whole real line, so I don't have to worry about anything. This is fine. So anyway, it gets there, and then finally substituting the u back with u equals x minus b, this turns into a Taylor series centered at x minus b. And I can actually check this pretty quickly, just like we did with e to the x, because derivatives of sine are not too hard to do, right? The derivative of sine x is cosine x, and then the derivative is minus sine x, and the derivative is minus cosine x, and the derivative is back to sine x, and it repeats every 4 things, right? And so I can notice here that this is just the sine with b plugged in. The derivative would be cosine of x, but with b plugged in. The next derivative would be minus the sine of x, but with b plugged in. And then minus cosine of x with the b plugged in, back to sine. So yes, this is the Taylor series for the sine of x centered at x equals b. Okay. So with this notion of composition from the last video, we can see how to change from Maclaurin series into Taylor series centered at other places. For some functions, right? We have to really know what the algebra of the function is when you handle a u plus b. I knew it for sine. I knew what to do with this 1 over 1 minus x. That was easy enough to do. And we had the property of the exponential up on the top that allowed us to handle an e to the u plus b, right? We knew what to do with it there. Other functions, I may not have that, in which case this method doesn't work. But at least for these, it does.